Okay, so let's resume from a couple of remarks about quantum Hall effect of last lecture. I want to tell you about anomaly in flow. Okay, so we had this geometry, okay, and we have a variable here, okay, and then the point is that on the edge theory there is a no conservation of the charge, okay, no conservation of the charge, but in fact the charge is conserved in the entire system, okay, because this is the all current orthogonal in the direction, radial direction, that goes through, okay. So if you combine the two, there is a conservation of charge, of course, right? And so the anomaly in flow is what we say that there is a system, there is a quantum system, okay, 1 plus 1D, which is anomalous, but this anomaly is compensated by a 2 plus 1D bulk, which is another system which attached to it, and this anomaly is given by a classical current, okay? I mean, this is an example of compensation of anomaly globally on the system. The system is non-relativistic, so it's there is no anomaly globally, so the charge is conserved, and so the anomaly comes, the non-conservation comes because you consider a subsystem, and then you limit yourself to the charge at the boundary, but considering the charge of the bulk and the boundary, there is conservation, okay? So this is part of several properties that exist in topological states, topological phase of matter, which is the bulk. This is one instance of bulk boundary correspondence. What are the other instances? Well, the symmetries, the nature of the degrees of freedom, the combination of the relation between the observables, the relation between the effective theories in the bulk and the boundary. Okay, this is elevated to a paradigm. Can be elevated to paradigm. You say, okay, whenever I have an anomaly, maybe there is a bulk that compensates for it. So that in total, there is no anomaly, okay? So for example, I have anomalies in 4 dimension. I say, I believe that there is a 5-dimensional bulk somewhere that will compensate, okay? Some people can say, okay, this is an indication that we have a 5th dimension, okay? And why not? You're puzzled, eh? So in words you have this, you have the bulk theory, no, that so the response action after integrating the gauge field is 1 over 4 pi k ADA, okay, where this is writing in terms of forms, okay, A is A mu dx mu, and this stands for exterior derivative and product of forms, okay? So the induced response action, which is the whole current, okay, can be called bulk current, mu is derivative of S with respect to A mu, which is 1 over 2 pi k epsilon mu nu rho d nu a rho, okay? So this is the whole current, okay? If I take the spatial component, I get that this is the all conductivity, sigma h, okay? Okay, now you say, okay, if conservation of charge is what? You take a circle here around the boundary and you compute the flux, okay? So you say the flux over this circle of this radial component of the bulk, okay, is what? Should be the derivative of the charge, okay? This is flux conservation, okay? For this region here, okay? Okay? Because it should get out. If there is a flux entering, it should get out here. So that becomes the charge of the edge, okay? In fact, okay, you see that this is simply d0 of dx of d0, j0 of the edge, okay, that you can rewrite as dx d mu j mu, because the axial part, this is periodic, the axial part is absent, and okay, and in fact it is expected value 2 pi k. This you take r component, so you say, okay, if I take the r component here, this will be r, and then you will have alpha beta, where alpha and beta only take two-dimensional values, okay? And so you get epsilon alpha beta, the alpha a beta, which is the anomaly, okay? This is a form of the anomaly, okay? This is the anomaly, actually 1/2 of it. It's 1/2 of it, because we only counted the charge which excess here, not the one which diminish here, okay? In the anomaly, you sum the two, but here you only consider one, okay? Okay? And so you know, there is also this technical fact that anomaly is a quantum effect on the edge theory, but is compensated by a classical current in the bulk, okay? So people believe that now that whenever there is an anomaly, there is a bulk, corresponding bulk topological theory which compensated for it. The two things are the same thing. They came into pair. So whenever there is an anomaly, in general, in a system, there is a bulk system attached to it where a topological theory provides some effects which compensated for it. Okay, that's a general idea of anomaly in flow. Okay? This is believed a general fact, at least at technical level. Then whether it exists, this bulk or not, it's just an artificial thing. We don't know. But technically, this is very useful to understand the properties of anomalies. Also because anomalies, they are connected in dimension. We will see later that the anomaly correspond in different dimensions. They are all related by a chain of relations which connect anomaly in d plus 1, d plus 2, and they are all related because basically the mathematical property of this object, they are all interrelated. Okay. So that's anomaly in flow. Okay. Then let me discuss a bit the thermal current, which is another effect of anomaly. I already said something about it. So what's the idea? We take again this geometry. Okay. Let me make a longer thing. And then we make a cylinder. Okay. With this. And we identify the thing. Okay. Okay, and similar here there is. Okay, so a way to introduce temperature, maybe you know, is to make time Euclidean equal to beta, which is 1 over kb temperature. Maybe you know this, right? If I take a theory, I put Euclidean time equal to beta, then I have I have the usual evolution in time becomes a Boltzmann weight. Okay. Okay. So then we can use we can consider the limit in which the length is much bigger than beta. Okay. So actually, we are we are kind of reversing space and time, because there are two circles, okay? One is L, one is beta, and we take that L is much bigger than beta. So we somehow switch time with the space, okay? Okay, then there is this fact that the energy in the ground state energy, ground state energy is different from zero and is given by beta, and this is called Casimir effect. Okay, so whenever you have whenever you quantize a field in a finite volume, there is some zero ground state fluctuation which are different with respect to infinite volume. This is called the Casimir effect. Okay. So we now consider the Casimir effect for the fact that this beta is finite, okay? While the L is taking very large. So we somehow consider that this is kind of a very large strip, okay? And this Casimir effect is related to the gravitational anomaly. Which I already introduced before, but let me repeat. And this is scalar curvature. The relation is a bit technical, and so I cannot tell you. I cannot tell you right away. It's not easy to get, but it is explained in the review, and so it has to do with the transformation property of the stress tensor. Stress tensor, the energy density. Energy density is a component T00, as you know, and the momentum density P is T01, okay? So the energy density, the stress tensor transform in a strange way when you map an infinite plane to a finite domain, transform in a strange way because of this anomalous pieces, and then you get a non-zero value, okay? That's basically the idea, okay? Then I can say that the energy in the ground state, which will be a constant, okay, is just P over C 12 beta square, because there is an additional integral in beta, okay? This is a density, okay? Energy density. And because the system is chiral, I also have a zero momentum in the density, P0, okay? And so P0 is equal to PC over 12 KB square T square, yes. This is a ground state thermal current. Okay, ground state values like this are kind of not well defined in quantum field theory. But because you can kind of redefine the energy, as we saw, you can redefine the energy we subtracted in the case of the Dirac here, we subtracted an infinity from the ground state, an infinity of charge, an infinity of energy. So you are also allowed to subtract a finite value. Okay. So in general, these final ground state values are not well defined. But what you can define is difference between two geometries, different between two parts of the system. In this case, they have a physical meaning. Okay, not the absolute value, but the difference. Okay, so in this case, we are going to make a gradient of temperature here between in the two edges, okay? And so there will be a gradient of currents, so different current, okay? Different currents in the two edges. So in this case, the difference makes sense, okay? So the difference is given by, to first order, is given by the derivative. So we get that delta P0 is 6 delta T, okay? And this is called, this coefficient is called KH, I'll say KH, okay, which is thermal Hall conductance. Thermal Hall conduction, okay? Because you see it's orthogonal, no? You have an extra current in one edge with respect to the other, orthogonal to the gradient, okay? Here there is a gradient of temperature, and there is a orthogonal current that is produced, okay? Okay, so this is another exact prediction of the anomaly, because C is this anomalous thing, okay? And that's very also supposed to be exact as much as the all current, all conductivity, because it's coming from anomalies that don't get corrections, okay? This is also related to topological thing, because this R obey the Euler Euler invariant. Okay, maybe you heard about this. This Euler characteristics. Yes. Yes. How the temperature? The temperature here is different. So beta is slightly different for the internal circle, than the outer circle. Yes, yes, yes. Or longer, yes. Through this, okay. So we'll have you will have a cylinder for beta interior, and another cylinder slightly different in size for the other thing, okay. Conformal field theory is only applies to the boundary, so you don't care about the three-dimensional object, okay? One conformal field theory here, another is here, okay? They're embedded in larger space, but that's not important. Yeah. Yes, yes, yes. Okay. So interesting thing that if you have this applies to this filling fraction, which was called the Laughlin edge, okay, Laughlin states, and we saw that on the boundary you have a chiral C equal to 1 theory, okay. But there are maybe we said that there are more complicated edges, like 2/3 and 2/5, which in fact they involve two scalars at the boundary, okay? And in 2/5, in 2/3, in 2/5, the two go in the same direction, and so you have that C and C bar, which are chiral antichiral anomalous coefficients is 2, 0. And in 2/3, they are counter-propagating, so you get 1, 1, okay? And in case you have a counter-propagate, you have different edge modes here, which are propagating or in one direction or the other. The formula is changed here because if you have a contribution to energy, they add up, add. Okay, so in fact, if you have if you have a different chirality relation is that A0 is plus or minus P0 according to the fact that they're left moving or right moving, okay? Because these are left moving, right moving. So if you have the other chirality contribution to energy adds up, but is subtract for the momentum, okay? So the more general formula here is that you have C minus C bar here. So in particular, for 2/3, you should see no current. Okay? Okay? For 2/3. And while here you get twice. Okay? The value. Okay? And this has been verified experimentally. Okay? So all of this has been verified experimentally. So it's a very nice result of this general idea of effective field theory, boundary bosonic theory, anomalies, and so on and so forth. This has been verified experimentally. So let me also mention that fractional charge has been verified experimentally in 97, I think. That gave the Nobel Prize to the Laughlin and the experimentalist of the fractional effect, and also fractional statistics. It has been verified, but only very recently, which is probably 21 probably. So it's amazing that it took so much time, because this system are you have to make a system very stable and to really to get results which are not spoiled by all kind of effects. So and also this thermal conductance is also recent in the last 4 or 5 years. So 19 to 23, it has been verified. Okay, so that's a very nice application of quantum of anomalies to condensed matter system. Okay, we're able to follow, please. Yes. Yes. The fractional charge is for nu equal 1/3. You have fractional charge Q 1/3 and fractional statistics e to the 2 pi over 3. So it's fractional statistics. Yes. Of course, they are not free. They are not free particles. You cannot say there is an action for free anyons. It doesn't exist. They are quasi-particle. Their microscopic theory or wave equation does not exist. And so the way you can describe it by doing these effective descriptions, okay, based on Chen-Simon and bosonic theory and this type of things. Okay, please. Yes. Yes. So it's you know, you have to. It's very very sophisticated experiment. You have to make a chip, because this electron move freely, in a layer, inside the layer, inside the superconductor. So through doping, you allow some electron to move freely into this layer. Then on this layer, you have to build some kind of strips that represent the different edges, and somehow you have to give a different temperature and measure the signal you get. Okay, so it's highly non-trivial, but it has been done, and so I don't have time to explain. But fractional charge was very easy to do. That was the first thing. But these other are more technical. These thermal law conductance and fractional statistics are more technical too. So, but it's true, okay? Okay, now we go to another subject. So basically, we're trying to explore a bit a new continent, which is topological phases matter in D bigger than 2, okay? Okay. So that was, there is a long story about this, and no, maybe I do another subject before. No, sorry, change of program. So first, let me do the technical part, okay? Technical part is the chiral anomaly in 3+1 dimension. So first technicality and then application, okay? That will be better. Chiral anomaly. So I don't derive it because it takes time. I just tell you the result, okay? Well, you have a Dirac fermion, okay? Again, it has two symmetries, no, and two currents. One is the U1, and which is related to charge, and there is another U1 related to axial charge, okay, as before. And the corresponding current are the same form as in 2 dimension, okay. But now you have a 4-dimensional spinor, 4-dimensional representation of gamma matrices, and so on, okay? Okay? Even in this case, you can decompose, because gamma 5 is a additional gamma function, gamma matrix, which anticommute with all of them and takes, and the square is 1. So you can produce a projector as in 2 dimension that split the fermion in 2 components. Okay? Okay? And what is the meaning of these 2 components? Each component is called a Weil fermion. Weil spinor. So 1 Dirac is equal to 2 Weil fermions. Okay? Split in 2 Weil fermions if mass is 0. So mass equal to 0. Okay? It's a symmetry for mass equal to 0. Okay, what is the meaning? Well, if you look into the solution of the Dirac equation, you discover that gamma 5 is this quantity. Okay? Okay, by definition of pi plus pi minus, you find that gamma 5 pi plus pi minus is plus or minus, okay, by definition of this projector. Okay? Recall that the project, if you call this P plus minus, projector has to be idempotent, I don't know how to say in English, and decompose into decompose the identity, okay, and be Hermitian, which is true because gamma 5 is Hermitian, okay. So this is a property of a projector, okay. Okay, what is the meaning? What is the meaning of this? This is a projection of the spin on the momentum. So this phi plus is a fermion which has some momentum and the spin along this. Okay, spin along this, and psi minus instead is anti-parallel. That's the meaning of the two chiral components. Okay. The name chiral, I think, comes from Greek and refers to handness, okay? Because S is a pseudoscalar, so it has to do with the, this type of thing that you do. These type of things you do when you start studying electromagnetism, no? You start to, first time you start to play with the hands when you study electromagnetism. Okay, so what is the anomaly? Well, the anomaly is this equation. Okay, so what is it? Well, it's kind of unique expression because you see, this is a pseudo vector. So if I contract this, it gets a pseudo scalar. So you have to have a pseudo scalar, which is gauge invariant. So it's made of f mu nu because it's gauge invariant. It's a pseudo scalar. It has dimension 4. Okay, dimension is 4. Okay. There are no dimensions in the theory because mass is 0, so only dimension is coming from the dimension of the fields. The field has dimension 3/2, okay? Because the Lagrangian is psi bar d slash psi, so this dimension 3/2, okay? So the current has dimension 3, this makes dimension 4, so the only thing you can make, which is a pseudoscalar of dimension 4, is this. It's a pseudoscalar because of epsilon. Then it has to have a E square, of course, because it's quadratic in the external field. Okay, that's good. So the only non-trivial part is the coefficient. So this coefficient here is the exact part, which is very important. Okay. And there are several reasons why this coefficient, like in 2 dimension, cannot be anything else than what it is, okay? Why so? Because again, there is a relation with the topological quantity, which takes integer values, okay? Okay? So we are going to discuss, in a moment, we discuss again the spectral flow. And we will see that if I make a change of charge equal to 2, the quantity which generates this is given by integration in space-time of this. It must be an integer, okay? So integration of this would give e square over 16 pi square. Integration in time and in space of okay? So the argument is that, as before, is that if these two configuration of the fields at plus and minus t during the adiabatic process you do to create this spectral flow, they differ by a large gauge transformation. I can compactify this space, and so I get that this quantity 1 over 32 pi square integral on a compact manifold in 4 dimension is an integer. Must be an integer. Because this makes 2, and so the spectrum returns to itself. So this is a large gauge transformation, and this is possible to compactify, and this you get an integer. That's the same reasoning we had in 2 dimensions, okay? Okay? And so this is another topological invariant. It's called second Chern class. Or if you want also instanton number. Okay? This is another quantity which, for any field configuration, is integer. And is invariant under smooth deformation. This is a topological invariant. So it's basically the square of the monopole charge of the monopole, because the monopole was 1 over 4 pi epsilon mu nu f mu nu element of z. Okay. So it's basically the square. Okay. Let's check this. Okay. We check that this is the square of this. Yes? E square, I put it to 1. Okay? Put it to 1. Let's check it is so that this strange number fit with this number. So somehow we got used that this number is correct, okay? Because related to the flux quantum, and so we understood that this was correct number. Okay? Let's check this is also a correct number, okay? So we're getting familiar of this. Okay, let's evaluate this quantity for the following compact thing: S2 cross S2. This is a possible compact surface in 4 dimensions. Okay, why not? So if this is integer, it should be integer for any compact manifold. Okay, so let me try this direct product of two spheres. Okay. Okay, and so what is it? Well, okay. So you see, you can say, oh, look, I can take two coordinates to the first sphere and 2 for the second sphere. Why not? Is a direct product of spaces. Okay. Okay. Then this will be 1 over 4 pi integral S2 di f mu nu epsilon mu nu, okay, square, which I know is an integer, okay. Then I have the remain 1/2 here, because this is 16 and you have 32. But then there is a factor of 2, because I can switch, no? Because any of these pair takes the value 1, 2, 3, 4, and so there is a possibility, there is a contribution twice this splitting. Okay, fixing. Let's say that this is coordinate 1, 2, and this coordinate 3, 4. There is a factor of 2. Okay. Okay. And so knowing that this has a value of n, this must be n squared. In particular 1. Okay, so I have checked that this is correct normalization of this object. Okay? Yes, please. Yes? This is a high energy name. This high energy name. Yes? And it is indeed also appearing in topological matter, but that don't discuss this. But yes, so this there is a tunneling process. Yes, yes, yeah, yeah. But the point is that once you are given the group and the space, so once you are given the group U1, abelian, and then you are given the space which is 3 plus 1D, the possible structure of this thing is fixed, or if you have a non-abelian group, is charted. So you know which of these objects you have. That's a geometrical problem that has been solved. So since this structure is unique, it appears in many places with different names, but it's always the same mathematics. Okay. So let me now discuss the spectral flow. The spectral flow setting is very simple. I mean, not discussing full detail, but just to give you a flavor that what it is. Okay. Well, if I can rewrite this anomaly equation like d mu j mu equal to 1 over 2 pi square e square, 2 pi square e dot b. Because you know that f is a tensor made by E and B, and so you work out what it is, this product, and you get that it is this value, okay? So this has to be compared with the 1 plus 1D that we said that d mu j mu was E over 2 pi E, okay? There was some E in the direction of space direction, okay? So the idea is that if you want to get the same setting, you can of which mimic the case we know already, which was this flow of along the bands of the Dirac field. You can realize by putting B, a constant B, in one direction. So let's take a B is BZ, okay, in direction Z, constant. Okay, so then the problem splits into a spatial motion and a motion in direction Z. Okay. So if B is a constant, then it looks like a 1 plus 1 dimensional equation. Okay, you see. In fact, it does. It does because if I take a fermion in 3 dimension, okay, fermion in 3 dimension, the motion orthogonal, the plane orthogonal to B will be this winding around of in a magnetic field. Okay, in these orbits which are okay. The xy part of the motion will be the usual orbits. Okay, so you have Landau levels. So here you have Landau levels. Okay. Instead, if the electron moves along the magnetic field, it doesn't feel the magnetic field. Okay. So that will be just a free motion with momentum pz. Okay. Okay, if you work out the Dirac equation in this background, you find the following. It's not too difficult, but not so difficult. That you will have energy which depends on Pz, okay, which is free, like a free particle, and then you have Landau levels with respect to the other coordinates, to the other directions, okay. And is also relativistic because we are dealing with relativistic. So you're dealing with relativistic dispersion relation, okay, which is Pz square plus the energy of Landau levels, which is 2n plus 1 b. Okay, so there is a Landau level index, but also we have the spin sigma, because the spin of the thing can be aligned along B or anti-aligned, okay? So there is a contribution, and sigma is the spin along in sigma z, okay? Sigma z, so it is sigma is 2sz, it is plus or minus 1, okay? So the spectrum is like this, okay? And this plus or minus the square root of this is due to the relativistic dynamics, okay? Okay, this is, I give you as I don't prove it, but it kind of not so impossible to digest, okay? So you see, you have different branches here, and n equal to, of course, 0, 1, 2, etc. Okay? And also there is a plus or minus, so you have a reflection of the spectrum up and down. The point is that this piece looks like a mass. It's like a mass term. So in general, you will have a parabola, okay, but not but unless the case in which this is 0, and this is 0 when there is a special lowest Landau level in which n equal to 0 and sigma is equal to minus 1, for which this is 0. Okay? So there is a pair of branches which are like relativistic, and the other are massless relativistic, and the other are are like massive. Okay, so there is a single spectrum like this, which is this case, and then there are massive spectra which reflect up and down, which are like this. Okay, that's how it goes. With respect to the so with respect to the momentum pz, which is like a free particle. Okay, so basically you have a sort of many copies of a one-dimensional particle, but in some cases it has a massless, this case, and in other cases is massive. Okay. Now you feel the lowest. You feel all the Dirac C, so you feel all this. Okay, and these instead are empty. These bands are empty. Okay. So then, okay, in this situation, you switch on an electric field. You switch on an electric field, you will have the usual drift of states in the direction of the electric field. So you take a BZ, and then you put we switch on a EZ, okay, and so we have a drift. So we have a drift like this. Okay, and like this. Sorry, here I put, maybe I didn't put them correctly spaced, but you understand, okay? And then you have a drift like this, and also drift like this. Okay, but what counts for calculating the difference of charge here, what counts is only the state which pass through to the Fermi surface, to the Fermi level, okay? Because they move here, but they do not change the charge with respect to the ground state. They move here, okay? They don't produce any. The charge is when you promote an electron above the Fermi sea, or you bring it down. You bring a hole down, okay? Okay, so the motion is the same, and only the effect is only due to this lowest branch which crosses, these two crosses, which crosses the Fermi level. And so the mechanism is exactly the same as in 1+1 dimension. Okay? And if you compute the coefficient, then you will find that knowing this result in 1 dimension, you produce this result in three dimensions. Okay? So that's the idea. Did you get? Yes? No, because they remain below the, you see? Yes. But net change of energy is only due to this unique band, which is, you see, is massless. Here is what you produce by this adiabatic change of electric field. So adiabatic change, no excitations. Yeah, excited states, they can move here, yes. So provide you give sufficient energy, but it's not the kind of motion I'm realizing here. Yes. There are many of these, okay? Okay, so that's more or less what I wanted to say about 3+1 anomaly. Okay, and then I think we can stop now for a short break, okay? 5 minutes, yes. Okay. So now discuss application of this anomaly in higher dimension. Okay, so I cannot cover many things because of time. I just give you some flavor, and there are several applications of this formula. Okay, I just try to give you some flavor of what are the applications. Okay, at least in one case. Okay. So what was topological phases matter. Topological phase of matter in d equal to 2 and let's say other. Okay? So, I mean, beyond the quantum Hall effect, okay? Quantum Hall effect is kind of a model for all of this, but then there are many more. That is, as I told you, it was a kind of a boom of these things. So what is the reason? Well, first of all, you can have a piece of material without magnetic field. So first of all, you try to do 2+1 D matter, like a band insulator, a piece of matter, a slab of matter, band insulator, without B. Well, is it possible to have a situation like in the quantum Hall effect, that there is a bulk gap, but non-trivial topology, okay? And then boundary states, boundary master states. Yes, it is possible. Simply B will not coming from the external field, but will come from the Berry phase. So somehow in this band system, you will have some features that produce a non-trivial Berry phase, and then you will be able to construct the fast Chern class given by this Berry phase B. Let me call Berry phase, let me call differently like a curly B, okay? Okay, and then this will be over integrated over the parameters of the system. And what will be the parameter of the system? Well, the parameter, because if it is a two-band system, it can be modeled by analogy of the Hamiltonian that I wrote you of a spin Hamiltonian, okay? H dot sigma, okay? Because sigma is index for the two bands. One is field is a valence band. This is empty, is a conduction band. You have a gap. And this system can, with some approximation, can be modeled by this. But H will be a function, okay? H will be a function of momenta. And by going around this Brillouin zone, you will find that there is a non-trivial Berry phase that produces this number, which is an integer. So this is going to be over the Brillouin zone. So this is, in fact, 2p, okay? Okay? If you have such a situation, depending on the parameter of the Hamiltonian, then you can have a system which has the same features of the Hall effect, but without magnetic field. Somehow the magnetic field is produced inside the model by the parameters, by the fact that the parameters in the Hamiltonian are kind of skewed. Okay? And so this is was called Chern insulator. First example was given by Haldane around 96, I think. Chern insulator. So in fact, you find the whole current here. So you find the current when you put an electric field. You will find the current which is sigma E. Okay, you have a boundary current, and sigma is again given by E over H, E square over H times N, where N is the value. So depending on the phase space of your system, so depends on the parameter of the system, you will have a region in which this number is different from 0, and then you will have edge states with this current, massless edge states with this current. Okay? This has been also verified experimentally. Okay? So that was a first instance of a system that say that, okay, this idea of topological matter is also present in absence of a magnetic field. So much simpler, much more generic thing. But then it turned out that there is a tenfold classification of symmetry protected topological phases. This is abbreviated SPT. Okay. So what is it? This is that you take a more restrictive point of view. You say, I will have a material which has topological properties, means that I can deform the Hamiltonian, I can deform the space in which I am smoothly, but subjected to preserving a certain symmetry. So in the Hall effect in the chain insulator, there is no symmetry that has to be preserved. Once you have it, it's completely stable. So it would be the case, trivial case in this classification in which you don't have any symmetry to respect. But then there are also phases in which this phase remain stable with a gap, but if you break a symmetry, it disappears. Okay, what are the symmetries? Well, the symmetries are very generic symmetries, which are time reversal, charge conjugation, okay, these two. So you realize a fermionic system in a band insulator. In a band insulator, you have realized a fermionic system, and you can realize different. You can be this I call T, and this I call C. This can have a different. It can be absent. Okay. Like this would be the quantum effect. Both of them are absent. No symmetry. And if there is a symmetry, there are two possibilities, that t square squared to -1 or +1, and c square is plus or -1. Okay? So there are three possibilities here. Three possibilities makes 9 possibilities. Okay? But then there is one case in which they are both absent. So in fact, there is a third possibility. So the case is absent has two possibilities. So there is one and makes 10. Okay? So this was very interesting. Chain insulator and quantum Hall effect refer to this. Okay, which was kind of super stable. Okay, but then when you require that that the phase remain the same under smooth deformation while keeping a certain symmetry, then you get a refined structure, sort of like this. Okay. Okay. So this classification was not obtained using field theory. It was obtained by 3 different methods, not related to quantum field theory. So this was 3 different methods, not quantum field theory. Okay, and based on free fermions in band system. Okay, that was the result. Okay. Okay. So then what will be my goal? To show that this classification can be understood in terms of field theory, effective field theory, and anomalies. So the question that my question is, can I reproduce the 10 classes with low energy quantum field theory, like as we saw Chen-Simon, okay? Okay, low energy effective field theory, Chen-Simon? Yes? And then extend to interacting fermions. with anomaly. Okay? Because we saw that if we rely on anomalies, like in the fractional effect, I get the results also in interacting case, while these apply to free fermions. Okay? So, in some sense, the low energy field theory is effective, so it's not fundamental, it's not microscopic, but somehow can grasp what happens in interacting fermions. And in fact, in some cases, in interacting fermions, this classification is not correct. Okay? So there is a correction to do when you consider interacting fermions. It's not a dramatic correction because you know that in 3 dimensions, the Coulomb interaction among the electrons is irrelevant operator. Okay? So in 3-dimensional bulk, the band theory is very accurate approximation of free fermion because Coulomb interaction is irrelevant. So in normal condition, interaction in 3 dimensions among electrons can be neglected, and a free fermion picture works. But this is generic, and here we are discussing spatial systems. You start with a band system, but then you start to do very peculiar features, and so some cases, this general statement that interaction are irrelevant in higher dimension more than two spatial dimension, this is not a correct hypothesis. Okay. So that's a setting, general setting, and let me maybe I don't have much time to discuss this, but let me say a few things about the main actor in this class, which is topological insulators. Okay? This is the best understood of these 10 classes, apart quantum effect, okay? Okay. So how it is realized? It is a system, so let me take a piece of material, like a solid cylinder, okay? Okay? And so it's a chunk of matter, so it's with a solid cylinder. So we have a bulk gap, okay? And then we have a massless Dirac fermion. In 2 plus 1D here, on the boundary, okay? Okay. So what's the point? The special point of topological insulators is that they respect the time reversal. And T square is equal to -1. So it's a system which is topological as long as the time reversal symmetry is not broken. How could I break the time reversal symmetry? For example, making this system in contact with a magnetic material, which has some, for example, spontaneous magnetization. Spontaneous magnetization has spontaneous magnetic field. Magnetic field is a pseudo vector or pseudo scalar. Okay, so that induces a breaking. If I attach to this material which is magnetic, this induce, for example, on the surface, induce a breaking of time reversal symmetry. Then this system, it becomes trivial. What means become trivial? Means that boundary muscle excitation, which is the characteristic feature on the boundary degrees of freedom, become massive. Okay? So if you break T, then the boundary fermion, boundary Dirac acquire mass. Now you say, okay, why it is trivial? Well, because the bulk is massive, the boundary is massive, and then if I go low energy enough, everything is massive, no excitation, nothing moves, and so it's a trivial insulator. Okay? Okay? So what would be, so okay? So that's the idea, okay? If a characteristic feature of topological states is that they have massless excitation on the boundary. If for some reason they acquire a mass, then the phase disappears. The point is that the point here is that they don't acquire a mass if you don't break time reversal. So there is a theorem, okay? Okay. No T preserved mass equal to 0. This is due to Fou, Kane, and Miller. It's a very nice argument, which is related to Lafren argument. Very nice argument. So as long as you preserve the time reversal symmetry, the fermions on the boundary cannot acquire mass. Any interaction. So I'm not going to make this argument, but let's analyze simple cases. So you say, okay, I have a Dirac fermion. Why I cannot put a mass term like this? Well, you cannot put a mass term because this breaks time reversal. Okay, this breaks time reversal. When you first hear about this, you say, something fishy. No, it's not fishy. It's not fishy because we are in 2 plus 1 dimension. We are not much used to 2 plus 1 dimension. Okay? Okay? And the story is the following, that the fermions correspond among themselves in dimension in the following way. So in 4 dimension, so in 3 plus 1 dimension, you have a Dirac, which is equivalent to 2 Weil, okay? Because you have a chiral splitting. Okay? Then you say, let me do simple dimensional reduction. I take the Dirac equation. I say that the spinor does not depend on one of the coordinates. Simple dimensional reduction. Why not? Okay? Okay? Then you will see that one Weil is here, gives you a Dirac, and another gives another Dirac. Okay? Instead, if I take a Dirac, I get 2 in 2 plus 1, I get 2 Dirac. Okay? Okay? Then when I go in 1 plus 1 dimension, I take a Dirac, I produce 2 Weils. Okay? You see? So what is natural from the point of view of electrons is that Dirac electron in 3 plus 1 dimension, okay, which is of course invariant under T and C and has all the possible symmetry, and the mass is really something you can add. There is no problem. But when you go down in dimension, a Dirac split in 2 Dirac. Okay? So the mistake of this system is that to have a single Dirac on edge, which is not natural. Natural will be 2 Dirac, because inside here, when you bring an electron inside here and you put on the boundary, you will produce 2 Dirac. not 1. And so somehow this is a Dirac, but it's like half of what you would expect of for a particle, like in even dimension. You see. So in even dimension, you understand that there is this chiral splitting, and so you know that a vial is half of the electron. So it's kind of peculiar, half of it. In 2 plus 1, there is no chirality, but nevertheless, 1 Dirac is a kind of special thing, okay? Funny, eh? That's it. So in fact, this topological insulator is like the Hall effect in the sense that you have a second boundary here, let's say, second boundary. Then an electron inside here would split into half of it will be a Dirac here, and half of it will be a Dirac here. So they become splitted. And since they split, they don't get mass. This term is not possible without breaking T symmetry. Instead, if you have two fermions, then you can write a mass term which is respecting time reversal. Okay? So if you have two fermions, two degrees of freedom, two fermions on the boundary, then you can give a mass. Okay? And so the phase is trivial. The phase of matter is trivial. If you have a single one, it is non-trivial. So this topological insulator is characterized by a Z2 index. Okay? Z2 index is equal to the number of fermions on the edge of the boundary, number of boundary fermions mod 2. Because if you have 3 fermions on the edge, depends on your material. Your material can have several bands, several degrees of freedom, okay? So you have 3 bands, 2 can acquire a mass, and they remain 1. So it's non-trivial. If you have an even number, they can acquire a mass and become trivial, okay? So this phase is characterized by zeta index. Instead, the quantum Hall effect was characterized by a zeta index, which was the n of the Hall effect, okay? The n of the integer of the Chen class, okay? So it's characterized by a Z2 index. Well, you say, okay, but that was the story about the mass. Maybe I can create a gapped excitation with some other kind of interaction. No, that's a theorem. Any interaction which preserve interaction, free preserving any free preserving interaction, the mass is 0. Okay? Historically, this was like this. They tried several models, and they were finding sometimes massless, sometimes massive, and then they start to say, oh, there should be some reason for this. And eventually they found this general argument. Very nice work. Very nice work. Okay? Okay, so although it's the topological insulator looks like a normal thing, it is something special that this boundary excitation cannot acquire mass. Okay, so in the last 5 minutes, maybe, I give you the interpretation of this. I mean, I give you a flavor of the interpretation of this in terms of anomalies. Okay? And the interpretation is the following. Now, this is important. This is important. Okay. So what's the point? The point that I can say, okay, I have this, let me give a low energy description of this system. Okay, just the most trivial idea that come to my mind is to consider that inside this material I have a Dirac field with a mass, with large mass m. But this is 3 plus 1 Dirac, okay, in the back. Okay, so this 3 plus 1 Dirac will have such an anomaly if I put an external background. Okay, okay. 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 Then what I do is I write the Lagrange. I write this action, which is okay, and I do the following. I do a chiral transformation, so psi e to the I theta half gamma prime psi bar goes into. And I do the following. So if I do this transformation, the mass, so this part, which is the massless part, remains invariant because gamma 5 gamma 5 anticommutes to gamma mu, and so these two phases, this change sign and they cancel. But in the case of the mass, if you have a mass, the mass is not invariant, of course. I mean, it's not invariant, okay? But so the mass goes into e to the I theta gamma 5, the mass, okay? Because in this case, the phase does not cancel, okay? Let me take this for theta equal to pi half, okay? So this is cos theta plus I gamma 5 sine theta mass, okay? And so this is minus the mass. Okay? Okay? And then I do this transformation not everywhere, but only in a certain region. So I start from, let me take a picture of the radial part here of this system, okay? Radial part of the system. And then I say, okay, the mass, no, let me do this, okay. Radial system, I take the mass, okay? And so the masses start from this. I do this transformation in a region like this, minus m. So the mass now has this thing, okay? So inside the material, the mass is negative. Outside, positive. Okay, I pretend that this is a picture of my material, in which the external of the material, or if you want another material which is not topological, something else, the trivial phase is m positive. The non-trivial phase is m negative. Okay, could be another material which is not topological, for example, or you say vacuum is a trivial insulator. I don't know. Okay. Okay. Now, what would be the action inside the material? Well, the action inside the material will be with the plus sign here, okay, inside the material. But there is another contribution because this is a chiral transformation, and so chiral transformation is affected by this anomaly. Okay, so there is a contribution in the path integral coming from the anomaly. Okay, and so there is a contribution which is if I imagine to add a chiral background to the action and then I do a gauge transformation of this chiral background, okay, then there is a contribution due to the anomaly, which is minus theta d mu j mu. Okay? But d mu j mu is that thing. So the anomaly produce that tell me that the path integral is not, due to the quantum effect, the path integral is not invariant under this chiral transformation. Okay? And the result is that this is minus theta over 32 pi square f mu nu rho sigma epsilon rho sigma. Okay? So this change of mass has produced this topological term as a term into the action. Okay? Okay? Lost? Okay? Okay, then I say, but let me take the mass very large. So okay, this was delta S. Then maybe take the mass very large, so that I'm only left with energy below the gap, M. M is big. So this, the fact that this fermion exists is high energy. I remain with this is the topological part. This is a topological term. I can have this topological term into the action. So that's a sign that I have a topological phase, because I have a topological theory in the bulk, okay? But then you say, oh, but then you made a mistake, because this quantity is not time reversal invariant. This quantity is not time reversal. So it changes sign for T changes this. Let me call this, I don't know, I, this is I, okay, of A. Change sign. Yeah, but that's a trick. That's a trick. It changes sign, but because this is an integer, this is minus theta. If it is non-zero, this is an integer, okay? It means that theta is a compact, okay? And so there are two possible values which preserve time reversal symmetry, theta equal to 0 and theta equal to pi, which is also equivalent to minus pi because of periodicity. Okay? So this is an integer. Okay? Yeah, I wrote the coefficient right. Yeah, I wrote the coefficient right. Yes. This is an integer. Yes. It's okay. This is an integer. Okay. So this appears in the phase. There is a phase. So there is a phase in the path integral e to I s. Okay. There is a phase. So theta is equivalent to theta plus 2 pi, and so pi is equivalent to minus pi. So the two cases will be a Z2 possibility, so trivial phase, theta equal to 0. And theta equal to pi, the topological insulator. Okay? Two cases. Okay? And how can I make this to do with the fact that I have edge states? Well, it's very easy. If you solve the Dirac equation in presence of if you solve the Dirac equation in 3+1 dimension in presence of this step in the mass, you will discover that there is a localized massless state here. So another effect of this switch of mass is that you produce in this kink mass, you produce a fermion which is localized in one dimension and massless. Here one, and here another one. They are the two fermions. This is called Jakiv-Rebbi argument. So this system indeed has a massless fermion. So this is localized in the radial direction, but this is a 2 plus 1 Dirac fermion. Okay? Then I say the last thing and then I stop. Okay, then you say, okay, but is there a cancellation between anomalies in the bulk, in the boundary, as we saw in the Hall effect? Yes, there is, because this 2 plus 1 Dirac fermion has an anomaly, has a Z2 anomaly. Which is called parity anomaly. But in fact, it is also time reversal also anomaly. Okay? And what is the effect? So this is a global anomaly. So it's different. Global anomaly is different in the sense that you don't have a breaking of a continuous symmetry, so you have a breaking of a current, conservation of a current. You simply have a discrete group for which the partition function is not invariant. Okay? So you have a partition function which depends on your field A mu. And then this is not invariant under gauge transformation, under large gauge transformation. Under large gauge transformation, you get to minus z, which does not make sense. Okay, so what is that? How do you realize this? Well, because if you compute a loop calculation, if you do a quantization of this theory, quantize the Dirac, you find that there is a contribution to the effective action, which is the Chen-Simon term. Okay? And because this has k equal 1/2, is not gauge invariant. And this contribution breaks time reversal symmetry and parity symmetry. And there is a cancellation between these two, bulk and boundary cancellation. There is you can see because this term is just a total derivative. So what is bulk, boundary, anomaly, matching is because this delta S of bulk okay, can be written as a total derivative. So it's pi divided by 32 pi square. Then you get a factor of 4 because you say this is sigma okay? Because I put f dA, okay? Okay, and this can be written as 1/8 pi if you have a boundary. Okay, so in fact, this theta term or instanton number is what you need to cancel the anomaly that you get from a Dirac particle on the boundary. Or if you want to transport the anomaly of one boundary to the anomaly of the other boundary to cancel. Okay? So, conclusion is that also in this case, we can understand, we can have a model, a continuous model of this topological insulator, which is based on the anomaly in 4 dimension and the relation of the anomaly in different dimensions, 4 dimension, 3 dimension, and so on and so forth. The new thing is that the anomaly is a discrete symmetry. The anomaly breaks a discrete symmetry, which is slightly more technical, but is not in the end is not so different. You still have a spectral flow because in the end there is a large gauge transformation that is not that does not leave invariant the system, okay, and it leaves invariant Hamiltonian but not the system, not the ground state, okay. And so in general, for the other phase of matter, the other 8 classes that I did not discuss, you also have discrete global anomalies or the breaking of discrete group of a more technical kind, and this is still an ongoing subject of research. And in some cases, the tenfold classification of free fermions has been corrected by anomalies by including also interacting case in 1 dimension and 2 dimension, and so that's a kind of still active research activity. That's it. That's it. Thank you very much.